Welcome back. So we've been talking about inverse problems, and we use that as a method to approach the solutions to problems that generally look like this, where we have an observation y, an unknown signal x, error e, and some sort of observation matrix A that we can observe things through. And we found that we could, of course, get an approximation of x back by just multiplying by the inverse of A. But then we explored what happens if you have eigenvalues of A that are small or large, and the impact that that has or causes the observation error to have. Well, so far we've been looking at symmetric positive definite matrices, and there are actually a lot of reasons we would do that. But sometimes, in fact, there are a lot of reasons we might not do that. And so let's look at another set of matrices, or another aspect of this problem, you may say, where we have y is equal to ax as before, and y is in Rm, a is Rm by n, and x is Rn. So in this case, A doesn't have an inverse if R does not, or M does not equal N, because it's not square, and so we can't get it back. So we're going to use something else. We can use the singular value decomposition. So the singular value decomposition of A and in future we'll almost always just call it SVD, is given by A equal to U sigma V transpose. Okay, so in this one we have U is equal to a bunch of column vectors is an M by R matrix where UM are m-dimensional vectors, and they form an orthogonal and normalized set. So that U transpose U is equal to I. One thing to note is that U transpose does not equal I when R is less than M in general. So in that case we would get something larger. So if you had R entries of U, if you did U times U transpose, you could get R ones on the diagonal, but your resulting matrix would be M by N. And so if M by M, if M is larger than R, you would have a bunch of ones, then And then what? You'd have zeros, and so it wouldn't work. So there are vectors form an orthobasis for the range space of A. So those are all the whatever you multiply by A, the range space is the total space, total number of things that could come out of multiplying by A. Okay, so next we have this V. Let's talk about that. So V is a matrix with column vectors VR analogous to what we had for U. Vn are n-dimensional, and they're also orthonormal. Therefore, we have V transpose V is equal to I. And once again, in general, VV transpose is not equal to the identity matrix, particularly when R is less than N. So our Vn vectors also form excuse me, an orthobasis. For the range space of A transpose. Okay, so what is the range space of A transpose? All I can say is that in general, if this isn't intuitive to you, then you are normal. And it'll require some thought. The range space of A transpose consists of everything which is orthogonal to the null space of A. So in other words, the range space of A transpose is everything that A does not kill. Now finally, let's figure out about this sigma. In this case, sigma is an R by R diagonal matrix in which all the entries, the diagonal entries, are positive. So it's going to look like this. and we're going to call these sigma values, sigma r, are the singular values of A. And furthermore, we're going to have them sorted, as we also did with our eigenvalues, so that the largest one is in the upper left, and the smallest one is in the lower right. So that's generally our singular value decomposition. I should add at this point that there are other ways of defining the SVD. And so if you're using MATLAB or Python or some package, or you're looking in another book, you may see a different way of defining this. So the SVD is sometimes defined as, well, actually I'm just going to put it this way, with sigma is equal to sigma 1, sigma 2, sigma r, 0, zero, 0, 0, like so on. We'll talk about this later. But to give you an idea of what's coming up, how does this work? Well, this works because right now we have only R entries, where R is less than N or less than M, and probably both, in our V matrix. So our sigma matrix is basically the smallest matrix there. It's R by R, which is the smallest one. It's also possible to define that as a larger matrix. We're going to end up padding our V's with additional vectors, and then adding zeros in the SVD. So this is sometimes done. We'll talk about it later. But for now, that's the definition of the SVD.